Now we are going to discuss lattice vibration. These are atoms attached to each other, we assume by ideal Hooke's law springs. A lattice may be regarded as a regular arrangement of points which are joined together by perfectly elastic springs. A lattice may be regarded as a regular arrangement of atoms, which are joined together by perfectly elastic springs. Means springs which obey Hooke's law. With this model for the lattice, we can say that motion of every atom would be shared by all the atoms in the crystal, and crystal would vibrate as a whole or as a single unit. That is, motion of the atoms is coupled. So here you can say motion of the atoms is coupled. Means you excite motion in one atom and it will be transferred to all the atoms. The lattice may vibrate freely in its normal mode due to its internal energy, or it may be forced to vibrate under the effect of external forces. So, the lattice may vibrate freely in its normal mode due to its internal energy or lattice may be forced to vibrate under the influence of under the effect under the influence of external forces which may be mechanical. Such vibrations give information about thermal properties of solids. Thermal properties of solids, such as specific heat or thermal conductivity or external forces may be electromagnetic in nature. Such vibrations, such vibrations are are associated with acoustical, acoustical or some optical properties of solids, some optical properties of solids. Now we are going to discuss vibration of vibration of one-dimensional one-dimensional monoatomic lattice. Monoatomic lattice. In your syllabus, monoatomic and diatomic we have to discuss. This is n plus 2th, n plus 1th, n minus 1th, n minus 2th. This displacement is xn minus 2. This is xn minus 1. This displacement is xn. So this is xn plus 1. This being x n plus 2 and so on. This is the equilibrium position and this is the displaced position. So let us consider one-dimensional chain of large number of identical atoms. Large number of identical atoms means same mass, where each atom has identical mass m and is attached to other atom by ideal massless spring. Now here we assume that the last atom is connected with the first, so as to form a ring. This assumption is simply to make the chain endless. This assumption is simply to make the chain endless, so that all the atoms have identical surroundings. Identical surroundings. Such a discrete arrangement constitutes such a such a discrete arrangement such a discrete arrangement constitutes constitutes a non-homogeneous medium which is distinguished from which is distinguished from a homogeneous medium wherein wherein the line of atoms is wherein the line of atoms is continuous without any break in between, without any break in between, just like string. In case of a string, the line of atoms is continuous without any break. Now at the equilibrium, you can see in the figure, at the equilibrium, the atoms are situated, the atoms are situated at equally spaced, or you can write equally spaced sites represented by n minus 2, n minus 1, n plus 1, n plus 2, and so on. If the atoms are placed on x-axis with the atomic with interatomic spacing a, then the x coordinates of the corresponding atoms are given by n minus 2a, n minus 1a, na, n plus 1a, n plus 2a, and so on. Now when the vibrational motion is excited, when the vibrational motion is excited, the atoms will execute periodic motion about their equilibrium position and become the source of longitudinal waves, longitudinal waves which propagate through which propagate through surroundings in along 100 direction. Let at any instant of time t the displacement of nth, n minus 1th and n plus 1th atoms from their equilibrium position are xn, xn minus 1, xn plus 1 respectively. Now, assuming that only significant forces only significant forces between the atoms are between the atoms are due to direct nearest neighbors direct neighbors direct nearest neighbor interaction, the net force upon the nth atom in terms of extensions of two springs which bind it to the atoms n plus 1 and n minus 1 as we can write Fn is equal to beta xn plus 1 minus xn minus beta xn minus 1, or this you can write beta xn plus 1 plus xn minus 1 minus 2xn, beta being spring constant. Now the influence of atoms other than nearest neighbors such as n plus 3, n plus 2, n minus 2, n minus 3 is neglected. Now by Newton's law, Fn is mass into instantaneous acceleration. So our equation of motion will be m d2xn dt square is equal to beta xn plus 1 xn minus 1 minus twice xn. Question 3. Now equation 3 represents the motion of nth atom. Now this equation, second order equation, can be solved by considering the solutions of the type xn is equal to a exponential I omega t minus k, x coordinate is na. Make this as equation number 4a, where k is equal to 2 pi by lambda omega by c is the wave vector, c represents velocity of propagation, and na is equal to x coordinate of the nth atom. Now equation 4a represents a traveling wave, in which all the atoms vibrate with the same frequency, angular frequency omega, and have the same amplitude A. So similarly, for xn plus 1, you can write a exponential I omega t minus k n plus 1a. xn minus 1 will be a exponential I omega t minus k n minus 1a. This is 4b, 4c. ddt of xn gives you a I omega exponential minus I omega t minus kna, and second order derivative will give you minus omega square a exponential I omega t minus kna. This is 4a. Now from equation number 3 and 4, we'll substitute all these values. We get minus m a omega square exponential I omega t minus kna is equal to beta a exponential I omega t minus k n plus 1a plus a exponential I omega t minus k n minus 1a minus 2a exponential I omega t minus kna. This gives you minus m omega square is equal to beta exponential minus ik plus exponential ika minus 2 is equal to beta cos ka minus I sin k plus cos ka plus I sin k minus 2. This is finally 2 cos ka minus 2. It is 2 beta cos ka minus 1. Or this you can write omega square is equal to 4 beta by m sin square ka by 2. This will be 2 beta minus 2 sin square k by 2. So omega is root over 2 beta by m sin k by 2.